Welcome to the Deep Dive. Today, we're going to be taking you on a journey through the cosmos. We're exploring the world of astronomy and astrophysics. You shared an introduction to Astronomy and Astrophysics by Pankaj Jain. It's a textbook that's used at the Indian Institute of Technology in Kanpur, so we know we're dealing with some serious star stuff here.
Yeah, definitely. It's a great resource for grasping those fundamentals. And I think it'll be really exciting to kind of delve into its insights with you.
Yeah, so get ready to have your mind blown by the sheer scale of it all. We're not just looking up at twinkling lights, you know. We're going deep into the physics that govern these celestial objects. Did you know that there are some stars that are so dense that like a teaspoon of their matter would weigh a ton? Or that we can actually map the spiral arms of our own galaxy using radio waves?
It's incredible what we've been able to learn about the universe, even though we're just a tiny speck on this cosmic canvas. Just think about it. The structures in the universe range from our solar system to galaxies, to clusters of galaxies and even superclusters. And these superclusters are mind-bogglingly huge. They can span 10 to 100 megaparsecs. That's millions of light years across.
Yeah, millions of light years. It's almost impossible to wrap your head around those distances. But even from our little vantage point here on Earth, just looking up at the night sky, I mean, it's awe-inspiring, right? All those stars forming these patterns that we call constellations. Yeah. I mean, they've fascinated humans for centuries. I remember when I was a kid, just feeling the sense of wonder, like trying to spot the Big Dipper.
I can only imagine. I mean, every culture has projected stories and meanings onto these patterns, and the constellations that we're familiar with today, they come from the ancient Greeks. But the beauty of the night sky, it's like a universal language. And when astronomers talk about stars like Alpha Centauri, they're using those Greek letters to tell us something about their position within a constellation.
Right, like Alpha Centauri is the brightest star in the constellation Centaurus. But I guess it isn't always the case that the alpha star is the brightest, is it?
That's right. As our observation techniques improve, we discover stars that are actually brighter. But the original Greek letter designations, they kind of stick around. And it's not just stars up there, right? We've got those fleeting streaks of light, those meteors, those chunks of space debris burning up in the atmosphere.
Yeah, meteors. I feel like those are kind of these little reminders that space isn't empty, things are always moving and interacting up there. And they enter the Earth's atmosphere at incredible speeds too, like 10 to 75 kilometers per second. What always amazes me is that sometimes those meteors are part of a meteor shower, right? Meaning that Earth is passing through a whole dusty region of space.
Exactly. It's like our planet is plowing through this cosmic debris field, and it creates those spectacular displays of shooting stars that we see, and then we have comets, those icy wanderers with their long, glowing tails.
Right. It's like they're putting on a show for us. Speaking of shows, how do astronomers even keep track of all these objects zipping around? I imagine mapping the sky is kind of like trying to chart this constantly shifting landscape.
It's true. That's where the magic of celestial coordinate systems come in. Astronomers use a system that's similar to latitude and longitude on Earth, but it's projected onto what we call the celestial sphere. It's called the equatorial coordinate system.
Okay, so instead of north, south, east, and west, they use
declination, which is like latitude. It measures angular distance north or south of the celestial equator, and right ascension, which is analogous to longitude, which measures eastward from a fixed point called the vernal equinox. You can think of it as the celestial prime meridian.
So basically, it's like a grid system for the sky, right? It helps astronomers pinpoint the exact location of anything from a nearby star to a distant galaxy. Pretty ingenious.
It is. And to observe these distant objects in greater detail, we use our most essential tool telescopes.
Right, telescopes, those giant eyes on mountaintops, though I guess they come in all shapes and sizes. What's the main difference between the main types of telescopes, those refracting and reflecting ones?
Well, refracting telescopes use lenses to bend and focus light, kind of like those old pirate spyglasses you see. Reflecting telescopes, on the other hand, they use mirrors to gather and focus light.
So which type is better? Is it just about size, like bigger is always better?
Well, they each have their own strengths. Reflecting telescopes can be built much larger, which means they can collect more light and see fainter objects. Plus, they avoid a problem that refracting telescopes have called chromatic aberration.
Chromatic aberration. That sounds kind of ominous. What is that exactly?
You can think of it like a rainbow effect. Different
Right.
colors of light, they bend differently as they pass through a lens, which can create blurry images. Reflecting telescopes, they avoid that issue. But even with massive telescopes, there's a limit to how much detail we can see. And that's because of something called diffraction.
Diffraction. Fill me in.
So light waves have this kind of quirky tendency to spread out when they pass through an opening or around an obstacle, and this spreading causes a slight blurring effect. which limits the resolution of any telescope, no matter how large.
So even with our most powerful instruments, we're still limited by the fundamental nature of light itself. It's fascinating to me that even something as simple as starlight holds so much information about the star itself.
Absolutely. When we analyze starlight using a spectroscope, we get what's called a stellar spectrum. It's like a fingerprint that's unique to each star. It reveals its temperature, chemical composition, and even its motion relative to us.
Wait, we can tell all of that just from the light? How does that even work?
Think of a star's spectrum as a rainbow with these distinct dark or bright lines. These lines are created by elements in the star's atmosphere. They're absorbing or emitting light at specific wavelengths. And each element has its own unique barcode of spectral lines.
Okay, I see. So by studying these spectral barcodes, astronomers can figure out what a star is made of and even how hot it is. And I know there's a whole classification system for stars, right? Like O, B, A, F, G, K, M. Those letters tell us something about a star's temperature, right?
Yes, that's the Harvard classification system. It ranks stars from the hottest, which are the O stars, they're burning blue-white, to the coolest, which are the M stars, they're glowing a deep red. Our sun, for example, is a G-type star, pretty average in terms of temperature.
Right in the middle of the pack. So we can classify stars. We know what they're made of. But how do these giant balls of burning gas even form in the first place? And what happens to them over time? Do they just burn forever?
That's where we enter the realm of stellar evolution, the dramatic life cycle of stars. They're born from these vast cold clouds of gas and dust called giant molecular clouds. These clouds are scattered throughout galaxies, and they're the cosmic nurseries where stars ignite.
So these giant clouds are where the magic happens. What triggers them to actually form a star?
Well, it all starts with gravity. Imagine a portion of this cloud, much larger than our solar system, collapsing under its own weight. As it collapses, it fragments into smaller clumps. And within each clump, the material continues to fall inward, getting denser and hotter.
So it's like a cosmic snowball effect. The clump is gathering more and more material as it shrinks. So what happens when it reaches that critical point?
At a certain point, the temperature and pressure at the core of this clump, they become so intense that hydrogen atoms start to fuse together. This nuclear fusion, the same process that's powering our sun, marks the birth of a star. And the energy released from fusion pushes outward, counteracting gravity's inward pull.
So it's this delicate balancing act, this cosmic tug-of-war between gravity and fusion. And as long as that balance holds, the star stays stable. It shines for millions or even billions of years. The stable periods is what we call the main sequence, right?
Exactly. Our sun is currently in its main sequence phase, and it will remain there for several billion years more.
But what happens when a star runs out of that hydrogen fuel? Does it just quietly fade away?
Not exactly. Especially when you're talking about stars much bigger than our sun, things get a lot more explosive. But before we jump into those fireworks, let's dive into the specifics of our own star, the sun.
Okay, let's do it.
Welcome back to the deep dive. So before we explore the fate of those massive stars, let's take a closer look at the star we know best, our very own sun.
Right, we left off talking about a star's main sequence, that period of stability that's powered by hydrogen fusion. Our sun's happily chugging along in that phase right now. But what's fascinating to me is that the sun isn't just this uniform ball of fire. It has layers, right?
Exactly. The sun is a giant ball of plasma, and its structure can be divided into these distinct layers, each with its own unique characteristics. At the very center is the core. It's the sun's engine room, where the incredible temperatures and pressures allow hydrogen atoms to fuse into helium, releasing the energy that powers the sun.
So the core is where the magic happens. But then what? How does all that energy get from the core all the way out to us here on Earth?
Moving outward from the core is the radiative zone, where energy is transported through radiation. Photons, those little packets of light energy, are generated in the core, and they bounce around in this dense region, slowly making their way outward.
So it sounds like a long and chaotic journey for those photons. How long does it take them to escape?
It can take hundreds of thousands of years for a photon to travel from the core to the next layer, the convective zone.
The convective zone, what goes on there?
Here, energy is transported through convection, much like boiling water. Hot plasma rises from the bottom, cools near the surface, and then sinks back down, creating this Trinan motion. It's kind of like a giant cosmic lava lamp.
I love that analogy. And at the top of this cosmic lava lamp, that's what we see as the sun's surface, right?
That's the photosphere, the part that emits the light and heat that we feel here on Earth. And it's not a perfectly smooth surface either. You can see features like sunspots, those cooler, darker regions that are associated with strong magnetic fields.
I remember learning about sunspots in school. They're not permanent features, are they? They come and go.
Exactly. The number and location of sunspots change over time, following an 11-year cycle called the solar cycle. During periods of high activity, the sun can release these bursts of energy and charged particles, called solar flares and coronal mass ejections, which can disrupt satellites and even power grids here on Earth.
Wow. So the sun's activity can directly impact us here on Earth. That's kind of unsettling, but also amazing.
Yeah, it really highlights the interconnectedness of everything in our solar system. And we haven't even talked about the layers beyond the photosphere, the chromosphere and the corona.
Right, those outer layers of the sun's atmosphere. Tell me more.
Well, the chromosphere is this thin layer above the photosphere, and you can actually see it as a reddish glow during a total solar eclipse. It's quite a stunning sight.
I've seen pictures. It's like this fiery halo around the eclipsed sun.
Mhm.
And then there's the corona, the outermost layer, right?
Yes, the corona extends millions of kilometers into space, and here's the weird part, it's incredibly hot, reaching temperatures of millions of degrees.
Hey, millions of degrees. That's even hotter than the photosphere. Isn't it supposed to get cooler as you move further away from the sun?
That's one of the big mysteries about the sun. This temperature inversion in the corona is still not fully understood, but scientists think it's related to the sun's magnetic field.
So the sun's magnetic field is responsible for all sorts of interesting phenomena, from sunspots to solar flares to this superheated corona. What creates that magnetic field in the first place?
Well, the sun's rotation, combined with those churning motions in that convective zone we talked about, create electric currents. And these electric currents generate the sun's powerful magnetic field. It's a dynamic system that plays a crucial role in shaping the sun's behavior.
It's incredible to think about all this complexity happening right in our own backyard, cosmically speaking. But before we get lost in the sun's wonders, let's return to those massive stars that we touched on earlier. We left off with the question of what happens when they run out of hydrogen fuel.
Right. Unlike lower mass stars, these giants have enough mass to fuse heavier elements in their cores, going from hydrogen to helium, then carbon, oxygen, neon, magnesium, all the way up to iron.
It's like a cosmic pressure cooker, forging heavier and heavier elements. But iron is where things hit a snag, isn't it?
Yeah.
Because you can't fuse iron into anything heavier.
Exactly. Iron is the most stable element in the universe. Trying to fuse iron actually requires energy instead of releasing it. So when a massive star's core fills up with iron, fusion stops, and things get catastrophic.
Catastrophic in what way? Does the star just fizzle out?
Not exactly. Without the outward pressure from fusion, the core collapses in on itself in a matter of seconds, triggering a shock wave. That blasts the outer layers of the star into space in this spectacular explosion known as a supernova.
A supernova. That's where we get those incredible images, right? Those brilliant bursts of light that outshine entire galaxies.
Precisely. And these supernovae are responsible for creating and dispersing all those heavier elements that we find in the universe. Elements that eventually become part of new stars, planets, and even life forms like us.
So we're literally made of stardust, forged in the fiery death throes of massive stars. That's mind-blowing. But what about the core itself after a supernova? What happens to that incredibly dense leftover?
Well, that depends on the mass of the core. For cores up to about 3 times the mass of the sun, the collapse continues until it becomes a neutron star.
A neutron star? What's that like?
Imagine an object about the size of a city, but with a mass greater than our sun. Neutron stars are so incredibly dense that a teaspoonful of their material would weigh billions of tons.
Billions of tons. That's more than Mount Everest packed into a teaspoon. I can't even wrap my head around that.
Yeah, it's hard to grasp the sheer density of these objects. And they're not just dense, they also spin incredibly fast, sometimes hundreds of times per second, and have these incredibly strong magnetic fields. They're truly extreme objects.
Okay, I'm officially in awe of neutron stars. But what about those cores that are even more massive? The ones that don't become neutron stars, what happens to them?
Those massive cores collapse beyond the point of a neutron star, becoming something even more bizarre and fascinating. A black hole?
Black holes, the ultimate cosmic enigmas. They're these regions of space-time where gravity is so strong that nothing, not even light, can escape.
Exactly. And the core of a massive star, once it collapses past a certain point, it forms what's called a singularity, a point of infinite density, surrounded by an event horizon.
The event horizon.
Yeah.
It's a point of no return, right? Once something crosses that boundary, it's gone forever. It's both terrifying and mesmerizing to think about.
It really challenges our understanding of physics and reality itself. And what's even more mind-boggling is that these black holes, while seemingly destructive, also play a crucial role in the evolution of galaxies.
Really? How so?
Well, at the center of most, if not all galaxies, including our Milky Way, lies a supermassive black hole, millions or even billions of times more massive than our sun.
So these supermassive black holes are like the gravitational anchors of galaxies.
You could say that. Their immense gravity helps hold galaxies together. But they can also be incredibly active. They devour gas, dust, and even entire stars, releasing enormous amounts of energy in the process.
Right, those are the active galactic nuclei, or AGN, we've heard about. Those incredibly luminous objects that outshine entire galaxies.
Exactly. AGN are powered by these supermassive black holes gobbling up matter, creating these swirling accretion disks that are heated to millions of degrees and emit radiation across the electromagnetic spectrum. They're like cosmic lighthouses, shining across vast cosmic distances.
Wow. From the tiny atom to these supermassive black holes. The universe is a wild ride of scales and energy. But where does our own galaxy, the Milky Way, fit into all of this?
Let's shift our focus now. From the heart of stars to the grained structure of our galactic home, the Milky Way.
Welcome back to the deep dive. We've journeyed from the fiery hearts of stars to the mind-boggling density of neutron stars and the enigmatic power of black holes. Now let's zoom out even further and explore our galactic home, the Milky Way.
The Milky Way is a truly awe-inspiring structure. Imagine a vast disk about 100,000 light-years across. With the central bulge and these spiral arms swirling outward, we're located about 27,000 light-years from that galactic center, nestled in one of those spiral arms called the Orion Cygnus arm.
So we're not at the center of the action, more like out in the galactic suburbs. But I imagine even in the suburbs, there's a lot going on in the Milky Way.
Absolutely. Our galaxy is teeming with billions of stars, gas clouds, dust lanes, and all sorts of celestial wonders. And those spiral arms, those are the birthplaces of new stars.
So those arms are like the nurseries of the Milky Way. But how do astronomers even figure all this out? It must be hard to map a galaxy when you're stuck inside it.
It is a challenge, but astronomers have developed some pretty ingenious techniques. They use a variety of methods, including star counts, the motions of globular clusters, and radio observations of neutral hydrogen to kind of piece together this map of the Milky Way.
Radio observations, why those?
Well, interstellar dust, which is pretty common in the Milky Way, it blocks our view at visible wavelengths, but radio waves can penetrate that dust, allowing us to map the distribution of gas and dust throughout the galaxy. It's like having X-ray vision for the Milky Way.
That's pretty clever. It reminds me of how medical imaging uses different techniques to reveal different aspects of the human body. So by combining different types of observations, we've built up this picture of this massive swirling disk that we call home.
And it's just one of billions of galaxies in the observable universe. That brings us to the realm of cosmology, the study of the universe as a whole, its origin, evolution, and ultimate fate.
Okay, cosmology. This is where things get really mind-bending. We're talking about the Big Bang expanding universes and things like dark matter and dark energy, right?
Exactly. To understand cosmology, we need to kind of shift our thinking. From this familiar world of flat, unchanging space to this mind-boggling world of curved space-time, where gravity warps the very fabric of existence.
Curved space-time. That sounds like something out of science fiction, but it's the reality of our universe.
It is. Imagine the surface of a balloon. It's a two-dimensional surface that's curved in a third dimension. In a similar way, our three-dimensional universe can be curved in higher dimensions that we can't directly perceive.
So like a balloon being inflated, our universe isn't static, it's expanding. That's where the Big Bang theory comes in, right?
Exactly. The Big Bang model suggests that the universe began from an incredibly hot, dense state, about 13.8 billion years ago, and has been expanded and cooling ever since.
Okay, but what's the evidence for this Big Bang? Sounds pretty wild.
Well, one of the key pieces of evidence is something called cosmological redshift. When astronomers observe distant galaxies, they find that the light from those galaxies is shifted towards longer wavelengths, towards the red end of the spectrum.
It's like the Doppler effect, but for light. Just like the sound of a siren gets lower pitched as it moves away from us, the light from distant galaxies is stretched, making it appear redder.
Precisely. The farther away a galaxy is, the faster it's moving away from us, and the greater its redshift. This observation, first made by Edwin Hubble, led to what we now call Hubble's law, one of the cornerstones of modern cosmology.
So the universe is expanding, but what is it expanded into? That always trips me up.
It's a common question, and the best way to think about it is that the universe itself is creating more space as it expands. It's not expanding into any pre-existent space.
Okay, I think I'm starting to get it. So is this expansion going to continue forever? What's the ultimate fate of the universe?
That's a question that cosmologists are still grappling with. For a long time, they thought the expansion would eventually slow down due to gravity. It was like a cosmic tug-of-war between expansion and gravity.
But that's not what we're seeing, is it?
No. In the late 1990s, astronomers made a surprising discovery. The expansion of the universe is actually accelerating.
Accelerate. So instead of slowing down, it's speeding up. What could possibly be causing that?
That's the million-dollar question. Astronomers have attributed this accelerated expansion to a mysterious force called dark energy, which seems to make up about 70% of the total energy density of the universe.
Dark energy. That sounds pretty ominous. What do we know about it?
Not a whole lot. It seems to have a repulsive effect, pushing things apart rather than pulling them together like gravity does.
So dark energy is winning this cosmic tug-of-war, driving the universe to expand faster and faster. What are the implications of that? What does it mean for the future of the universe?
Well, one possibility is a scenario called the Big Freeze, where the universe continues to expand and cool indefinitely, eventually becoming a cold, dark, and empty place.
That's a pretty bleak outlook. Are there any other possibilities?
Another scenario, more speculative, is the Big Rip, where the expansion becomes so rapid that it eventually tears apart galaxies, stars, planets, and even atoms themselves.
Okay, that's even more bleak. So we're either facing a slow fade into darkness or a cosmic shredding machine.
Those are two of the leading scenarios based on our current understanding. But cosmology is a rapidly evolving field, and new discoveries are being made all the time.
That's what's so exciting about it. It's this never-ending quest for knowledge, pushing the boundaries of what we know about the universe and our place within it. This deep dive has taken us from the tiniest particles to the largest structures, from the birth of stars to the mysteries of dark energy.
And we've only just scratched the surface. There's still so much we don't know about the universe, which makes it all the more fascinating to explore.
Absolutely. Thanks for joining us on this incredible journey through the cosmos. I don't know about you, but I'm feeling inspired to keep looking up at the stars and asking questions. Who knows what amazing discoveries await us out there in the vast unknown?
The universe is full of wonders just waiting to be uncovered. Never stop exploring.